So the final component of this chapter is a model for the wind. And we've already taken the wind into account in our dynamic equations. We saw how the relative wind vector affected our forces and moments acting on the aircraft. But in this lecture, we're going to dive in and discuss how do we model the wind? How do we generate the wind that we've already been using? So let's go ahead and get started. As we start off, we're just going to remember the wind triangle. So we had v sub g. That was the velocity of how our vehicle is actually moving. We had v sub w, which we've mentioned a couple times, but typically haven't directly used. V sub w is just the wind velocity vector. And then in our dynamic equation, we had v sub a, which was our relative wind vector. Now that relative wind vector was quite important for defining the forces and motions that acted on our aircraft. And in fact, we used the side slip angle and the angle of attack to help us define those forces and moments. So now, this lecture, we're going to talk almost exclusively about this v sub w. So how do we define that wind vector? And the wind vector can typically be decomposed into two different components. We have the steady state component and we have the gust component. And we use the subscript s and g to denote the steady state and gust components respectively. So our steady state component is typically defined in the inertial frame, right? So that's why we have our superscript I for our inertial frame. And our gust components are typically defined in the body frame. Now, the high level of model of how we're going to generate this model of the wind is that we're going to take our v sub ws, and again that's defined in the inertial frame. We're going to transform it into the body frame. And now recall that this transform goes from the vehicle frame to the body frame. But the vehicle frame and the inertial frame are parallel, so if we're talking about a vector in either one, it's going to be expressed the same. So we could also say that this could go from the inertial to the body frame for that rotation. So the output, these are the x, y, and z components of v sub ws, now defined in the body frame. And we're going to input white noise into a transfer. We have this transfer function. And the output of that is going to be our gust model. So remember, this is our x, y, and z components of the gust. So these guys together make up w sub g in the body frame. So together they make up that vector, and we're just going to add these two vectors together now to get the resulting wind, right, is just our, well, I should have written it like this. Our resulting wind that we'll get out is v sub w sub s in the body frame plus, then we had v sub w sub g in the body frame. So that's the main idea of how we're going to do it. Now, there's a couple different models, and the book discusses one called the Kármán turbulence model. It's great for approximating the gust, but it doesn't produce a rational transfer function. So a good approximation for that model is the Dryden gust model. And the book describes this in some detail. One thing to note is that these L sub u, L sub v, and L sub w, and I guess they pop up in these two different locations. Just recall that these are known as the spatial wavelengths. And together with the amplitude, where it's defined, these values define the intensities of the gust in each direction. So together with the intensities and the spatial wavelengths, we can come up with these equations for the Dryden gust model. And there's a nice table for talking about what are good values for the Dryden gust model at different altitudes. So if you want low altitude, light turbulence, all the way up down to medium altitude with moderate turbulence, we know they give you what they mean in terms of the altitude, as well as what should each one of these parameters be equal to. Okay, so we have these Dryden gust models that then these equations, right, show up here. So the inputs to these equations are just going to be white random noise, and the outputs are going to be the gusts that we combine to form our total wind vector. Excellent. So one question you may have is, how do we then implement this transfer function? So this transfer function is a fairly simple second order transfer function. We can put it into state space. So this is in our Laplace domain, the top one is, and the second one is the time domain representation. Now the time domain representation is really nice for simulating forward in time. What we can do is then, this is the dot notation right here. This is a continuous representation. So we're going to convert it to discrete time, and this is just using the Euler update, right? So we have x of k plus 1 is equal to x of k plus ts, and this is just our x dot, or is f of xu, right? And we've talked in a different lecture about this Euler approximation to our dynamic update. So we have this Euler approximation. So we can get the transfer, this two-dimensional state space update, and then we use y sub k as our output for the system. Now you may be asking, how do we define these A, B, C, and D values? Well, we can just come up here, right, and see that we have S, and down here we have up to S squared in the denominator. So it's just the coefficients that are acting upon the coefficients of these equations right here. Define our A, B, C, and D. So this guy, if we were to look at this equation right here, right, so we'd have this guy would be our A, multiply this by this guy will give us our B, then we'll have to multiply that out to get our C and our D values for below. Excellent. So now we have these nice transfer functions for generating our wind gust models. We have some tools to help us implement that. And then we just add in the effect of wind, right? So if we're going to get the wind in the body frame, this is just a summary, right? This was our steady state. And this guy came from the output of our Dryden models. And then we have our relative wind vector right here, expressed in the body frame. So this was right here, this is our V sub G, and this guy right here, is our V sub W in the body frame. Excellent. And then we can find our relative wind speed using this relationship, alpha using our ATAN, our inverse tangent relationship, and then beta, recall that in chapter 2 we actually defined a inverse tangent relationship for beta as well. So So we can now calculate our wind at each point in time, calculate our relative wind vector, and that will help us calculate our dynamics. So putting it all together, now here's a summary of our dynamic equations, where we have our gravity, we have our longitudinal lateral aerodynamics, we have our motor thrust and torque, or our propulsion. Okay, and similarly for the moments, we don't have any gravity effect, but we have our aerodynamic and we have our motor torque. And again, a huge factor in these is we have our angle of attack, and we also have our side slip angle jumping in all over the place, right? So now that we've produced the wind, we can go through and we can calculate what alpha and beta are. And from that, now we have everything we need in order to calculate the forces and moments acting upon our aircraft.